Hello, in this lesson we are going to discuss stoichiometric calculations. So the key questions that we're going to investigate is how do mole ratios work? Um, what are they? We established last time. Now we need to know how to use them, how to put them into action. Secondly, what is the general procedure for solving a stoichiometric problem? Um, that is going to be the biggest takeaway. If you learn one thing from this lesson, I want you to know procedurally what we need to do to solve a stoichiometric problem. I'll make it clear when we're going through that process. So you're just going to really want to make sure you have a solid understanding of that. A mole ratio is a conversion factor, namely the one that we find in a balanced chemical equation by comparing coefficients. A mole ratio is what we get when we take the coefficient for two different components of a balanced chemical equation and compare them. We use these mole ratios to convert between different types of chemicals in an equation. So we could start out with nitrogen and want to get to ammonia, as you'll see in a moment. And we would use a mole ratio to move from one of the reactants to a value for one of the products. Here's the start to a conversion. I pulled this out of the textbook and we'll talk through it for a moment. The first component or expression in this equation is what we know. We would be given some value, X moles of substance G, then times in a line. We'd be canceling out substance G and moving to substance W. The molar ratio is B over A, and B and A would be the coefficients found in the balanced equation. Assuming we were wanting to get to moles of W, then we'd be all done. We could simplify this by saying X times B over A, and that would give us our value for moles. This is a very general equation and an equation that I expect you have gone through before, but by the end of this lesson you should have a better understanding of what this is. So we are using the example of the creation of ammonia gas by combining nitrogen gas, 1 mole of it, with 3 moles of hydrogen gas. So the question here, using the same form as that generic expression we just talked through, how many moles of ammonia are produced if 3.5 moles of nitrogen gas react with excess hydrogen gas? Remember, since that we have excess hydrogen gas, we need to focus on the value from nitrogen. So we start with 3.5 moles of N2. Multiply this, and we need to come up with a conversion factor. We are canceling out N2, so we would expect moles of N2 to be the bottom part of the expression. And we are trying to get to moles of ammonia, so we would expect moles of ammonia to be the top part of the expression. The molar ratio is then pulled from the balanced chemical equation. Ammonia has a coefficient of 2 in the balanced equation, and nitrogen has a coefficient of 1 in the balanced equation. Now we can cancel out moles of N2, and we are in our final answer. We want to know how many moles of ammonia would be produced, and we are in moles of ammonia. So we put an equal sign and see that it would be 2.0 moles of ammonia. The problems aren't always this easy, unfortunately. There are a number of other things that can cause it to involve more steps. Oftentimes, the mole to mole using a mole ratio will be the middle component of a stoichiometric calculations. Oftentimes, either beforehand or after that conversion, we need to do a conversion with either mass, volume, or representative particles. For mass, we would use the molar mass of the substance involved. For volume, we would use the value of 22.4 liters per mole at standard temperature and pressure. And for representative particles, which would either be a formula unit, a molecule, or an atom, we would use Avogadro's number. To show you a little flow chart of how these might work. This could be a series of about a 3-step reaction or calculation right now. So we could start out with representative particles, mass, or volume. And our reactants are titled G, the capital G. This is being converted, or the reaction is producing W, as you see capital W. The coefficients are A and B. Okay, so you could start with any three of representative particles, mass, or volume. You would need to use a conversion to get to moles of G. Then, once you're in moles of G, you would use the mole ratio, as you can see in the middle of this flowchart, to convert to moles of W. Then once you're in W, you could need to change it to representative particles, mass, or volume. There are so many different permutations of this problem that I'm not going to do a sample one for this. There are many sample problems in the book. Check the comments for pages, as well as you are going to as well have an assignment that allows you to practice this. I fully recommend using your textbook to look through the examples and ask me questions, of course.